This is episode number 3, the periodic table. Now, the periodic table is organized by periods and groups. So periods are the rows here, and groups are the columns, right? Now, the periods, they go in increasing number of protons, right? So if you can refer back to episode number 1, we just talked about protons, neutrons, electrons. So this element is lithium, this element is beryllium, right? Now lithium, it has 3 protons, beryllium has 4 protons, right? So as you go to the right, you add 1 electron. And now neon, all the way to the end over here, you would go down 1 and all the way to the left and restart the process of adding protons, right? The elements in one period are trying to fill the same shell. So if you could refer back to our last episode, electrons, talked about shells and stuff. In period 1, the elements, hydrogen and helium, you can see there's only 2 because there's only 2 electrons in the first shell, like we discussed last episode, right? So hydrogen has 1 electron in the first shell, and helium has 2 electrons in the first shell. And of course, we're talking about neutral atoms of these elements. And we will be talking about neutral atoms for the rest of this episode. But, yeah. Hydrogen, 1 electron in the first shell, helium, 2 electrons in the first shell. Lithium has 1 electron in the second shell, right? And so now we've shifted from the first shell to the second shell. Right now we're filling the second shell. We jump to a new period, and now we have lithium all the way over here. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, all of these elements are trying to fill the second shell, right? Lithium has 1 electron in the second shell, beryllium has 2 electrons, and so on, right? And all the elements in one group have the same amount of valence electrons. If you could, again, refer back to last episode, valence electrons, they're the electrons on the outermost shell of an atom, right? So all these groups here, I'm sorry, it's blocking it here, but in this first group, they have the same amount of valence electrons, right? 1, because it's the first group. In the second group, you guessed it, it has 2 valence electrons. We're going to skip over these elements here, right? I'll make it a bit more apparent. Like these elements and these elements, because that's for later episodes. For now, we're only focused on the first 2 groups and groups 13, 14, 15, 16, 17, and 18. All the elements in group 1 have 1 valence electron. All the elements in group 2 have 2 valence electrons. Now we skip to group 13, and a fun trick to do here, there's exactly like 10 elements separating group 2 and group 13. So actually you could just take out the 1, right? So this is just 3, right? So group 13 becomes technically group 3 for now, and so it has 3 valence electrons. Group 14, take out the 1, 4 valence electrons. Group 15, 5 valence electrons. 16, 6 valence electrons. 17, 7 valence electrons, and 8 valence electrons, right? And now we can move over here to atomic squares. Now, this right here, this is the chemical symbol. So in chemistry, right, it's kind of difficult, not difficult, but tedious to write a chemical's name each time you want to refer to it. So we just use these chemical symbols right here. And you have to memorize them. It's just, as you learn more and more chemistry, you will memorize it automatically. But the periodic table is always at your disposal. But Yeah, this is the periodic square of fluorine, as you can see here. This is just the atomic name, and this is the symbol to represent it. Now this is the atomic number. This is the amount of protons that atom has. Now this is the atomic mass. This is the mass of the atom, right? For now, we're just going to round it up to the nearest integer, which is like just the nearest whole number. So 18.998, right next to 19. So the atomic mass, we can forget about electrons because they have barely any mass. So they're not going to be like useful for our calculations. We can forget about them basically. So if fluorine has an atomic mass of 19, and fluorine has 9 protons, how many neutrons is fluorine going to have? Well, no, protons and neutrons have the same amount of mass. So if it has 9 protons and 19 atomic mass, that means subtract the protons and we have 10 atomic mass that something else is taking up, which are the neutrons. So fluorine has 10 neutrons. So you would just round the atomic mass to the nearest integer, then subtract the atomic number from the atomic mass. So we figured out that fluorine has 10 neutrons. And finally, for this episode, I'll talk about an electron dot diagram. Now this doesn't have much to do with the periodic table, but we have to discuss it at some point, and I figured its own episode would be a little too much because it's pretty short. So these are the electron dot diagrams for a few elements, right? This is helium, beryllium, carbon, oxygen, argon. Now, electron dot diagrams display the amount of valence electrons an element has. And just saying, from now on, we don't really have to worry about the electrons that are in the inner shells of an element. We're more worried about the valence shells, and that's why the electron dot diagram only shows the valence electrons, right? Because those are the only ones really important. So helium has 2 valence electrons. Now helium, you might think that helium has 8 valence electrons because it's in group 8, but actually we put helium in group 8 because it has a complete outer shell, right? The first shell is special because it only has 2 electrons in it, while the second and third shell have 8 electrons, right? So helium is special. That rule I said about the amount of valence electrons of an element being equal to what group it's in for 13, 14, 15, 16, 17, and 18. Of course, remove the 1, but you get my point. That rule, it only doesn't apply to helium, right? We just put it here because it has a full valence shell like all these other elements, right? The noble gases. And so helium has 2 valence electrons. So this is how we would draw it for helium. So we have 2 electrons, right? And that's pretty simple, but the question is where to put them. So for helium especially, again, helium's kind of a special element in how, I guess, it's organized. So here, it has 2 electrons on the same side. So you can notice beryllium, it has 2 valence electrons as well, but it has them on different sides, right? Well, helium has a complete shell, right? A complete valence shell, right? So we would put them on the same side. Again, that's just special for helium. You just gotta remember that for helium. For the rest of the elements, it's pretty easy because this is the order in which the electrons go. First, you kind of put it on a random side. This doesn't really matter, but let's say we have element E over here. So first, we put a valence electron there. Then a valence electron there, then a valence electron there, then a valence electron there, and then when it gets 5 valence electrons, you start grouping them up. So valence electron here, valence electron here, valence electron here, valence electron here. And yeah, this only doesn't apply to helium because I just do 8 valence electrons there, right? But helium's valence shell is the first shell, which only has 2 electrons. So we would just draw it like this. And this rule does also apply to hydrogen in a lesser extent, but when we do chemical bondings, this would also be how you would draw hydrogen with a full valence shell. So beryllium has 2 valence electrons. It's in group 2. So we would first put it on one side and on another side. So this would be the electron dot diagram for beryllium. Carbon, so you put 1 on one side, 1 on another side. So 1 on all sides. Again, carbon's in group 14, which we're just going to say is group 4. So 4 valence electrons, so 1 on each side. Oxygen, 6 valence electrons, group 16. So it's going to put 4 on each side, and then it's going to start grouping up here and here. And now argon, it has 8 valence electrons in group 18. So it's just going to have 2 on each side. So to practice this, try to draw the electron dot diagram for aluminum. So pause the video right now and try it for yourself. Okay, time for answers. Aluminum, it's in group 13, so that means it has 3 valence electrons. Remove the 1. That means 1 here, and 1 here. Now, you can choose any side to start with, really. I mean, it doesn't really matter. But this rule for doing 1 all around, then doubling up is important. I mean, okay, that's not the electron dot diagram. Just wanted to demonstrate. But yeah, that rule is important for chemical bond. Now, finally, we're going to talk about the names of the groups, right? I jump back to the periodic table. So look back here. These elements in the first group is called the alkali metals. Sorry, this thing blocks it, but these are called the alkali metals. These are very reactive. These elements have 1 valence electron. So that means that they can just lose that valence electron so that it's happy, right? Because its inner shells are already filled, right? Electrons fill shells from inwards to outwards, right? So its inner shells are already full, so it can just lose that 1 valence electron. Now its valence shell becomes its inner shell, which is already full, right? This applies to all the alkali metals, right? But hydrogen, you might see hydrogen here, it's not the same color. Hydrogen is not an alkali metal because, think about it, if it loses a valence electron, it's just going to have no electrons, right? It would technically be a proton if you think about it, right? Because hydrogen has 1 proton. Its most common isotope has no neutrons. For now, don't worry about that. We'll get into radioactivity and isotopes later. But it has 1 proton, no neutrons. And if it doesn't have an electron, it'd just be a proton. So it doesn't want to lose an electron because then it's just going to have no electrons, right? I mean, that's bad. That's worse, right? Now, going on to group 2, these are the alkaline earth metals, right? So these elements have 2 valence electrons. Now, they're less reactive than the alkali metals because they have to lose 2 electrons now, right? Which is more work, technically, right? Basically, it's easier to lose 1 valence electron than it is to lose 2. So alkali metals are more reactive. So now moving on to group 13, 14, 15, 16. These groups, we don't really have a name for them. You can just call them group 13, 14, 15, 16. That's fine. But group 17, very important group, these are called the halogens, right? These elements. these elements have 7 valence electrons. They're group 17, so 7 valence electrons. Now, they are the most reactive group on the periodic table because all they need to do to be happy to get a full valence shell is to get 1 electron, right? So they really want to react because they're so close to being happy and having a full valence shell. And finally, we have group 18. These are the noble gases. Now, these elements don't react. So, like earlier I said, helium is part of the noble gases. It's because helium is like all these other elements. Helium does not react. All these elements have full valence shells, right? Elements react to get full valence shells, but they already have full valence shells, so they don't need to react. And I think that's about it for all I have for this episode. So, pretty long episode. So, just to recap, the periodic table is made up of periods and groups. Groups have the same amount of valence electrons, same properties, and periods have ascending atomic number, ascending amount of protons. The elements in one period are trying to fill up the same shell, right? In the second period, they're all trying to fill up the second shell. And the elements in the first group are the alkali metals. The elements in the second group are the alkaline earth metals. The elements in the 13th group, 14th, 15th, 16th, not unnamed. 17th group, the halogens. 18th group, the noble gases. Electron dot diagrams, except for hydrogen and helium, it would be 1 dot on each side. Then you would start to double up. And now, finally, atomic squares. This would be the atomic number, atomic mass, the number of protons plus the amount of neutrons. This would be the atomic symbol. This would be the name of the element. And you would subtract the atomic number from the atomic mass to find out the number of neutrons of an element. So that is going to be it for episode number 3, the periodic table. And I'll see you next time in episode number 4, ionic bonding.